better fidelity. The recordings have been coming out terrible. And so I thought if I use the desktop computer to record, you get a pop-up that says continue. You'll have to hit continue. Maybe we'll get better results. And I just had a conversation with ITS about the recording quality. It was so poor, it was embarrassing. And they said, well, I'll record on the desktop and then the desktop will give you better resolution. Or so they say. Or so they say. So we'll see. This is my big experiment. So welcome to another exciting computer architecture class. We've got a little bit of background to do, but there's also a homework assignment. And I think it was supposed to be submitted, is it tonight, end of day? Last night. Were there any questions about this homework? I believe it was the ginormous midterm.
Is it the midterm review?
Yeah. Yeah,
Okay.
the midterm, homework 1, midterm review, due last night.
The one that says homework 0 on the blackboard, right?
Does it say homework 0? I didn't know this.
It said I thought it said midterm review or something.
Yeah, it says homework 1. I can hold it up. You see? You see what it says?
Yeah.
It looks backwards to me.
Yeah.
But I think to you it looks forwards.
Yep.
So that's what I think you submitted. And the end of that sentence is I hope. And so at some level I could make a compelling argument that if that was homework 0, the next homework would be homework 1, but I thought it was homework 1, and that's how it's labeled here on this printout. And so the next homework that will be due is homework 2. That's what comes after homework 1. Or so one would think. So this is, I'll hold this up so you can see it. This is what we're doing now. This is on the Moore and Mealy machines.
You didn't post this yet? No.
Yeah, it hasn't been posted yet, but we'll post it today. In principle, I could post it right now, but I don't want to take time from class on that. And essentially, we're dealing with Moore versus Mealy machines. And one of the things that I wanted to emphasize is that when you're designing a computer, you're designing a machine that has a finite number of states, but that really just goes through a very small, I'll say, process, a small process. So a CPU is a finite state machine that does an instruction fetch, and I'll just write IF for short because I don't want to have to write it out, and I'll write nice and big. And then an instruction decode, so it's getting that instruction from someplace. It could get it from a tape, it could get it from punch cards, it could get it from memory. Modern general purpose computers get it from RAM. And then it does an instruction execute. And then after it executes the instruction, there is some result. And so what it will do is it will do an instruction store. So that takes the result and puts it out. And then it goes back to the beginning. So it's a quite finite state machine, isn't it? It's 4 states. And that's your CPU, and that's the whole thing. Very interesting. Why should have, yes?
What did the F and D stand for again?
Instruction fetch, instruction decode, instruction execute, and instruction store. Now, what drives this entire CPU process is a counter, a very simple counter called the program counter, PC. And the program counter essentially is a counter just like any other counter you might have encountered. Here it is, the program counter. And it has outputs, 1, 2, 3, 4. We'll just have a 4-bit program counter. Obviously, if you have a 16-bit or a 32-bit or a 64-bit machine, it would have that many bits. But we'll start with 4 because 4 is a nice small number and I can draw it. I have to draw 64, we're going to be here a while. And then it's got a little input in here called the clock, right? And what it does is it increments the counter, just like we expect. And it also has another input over in here called load. And that allows us to jam load the counter with an arbitrary address. And so it has to have 4 bits worth of input. And now what it does, in order for the CPU, right, to fetch an instruction, is it needs to get an address from the program counter. So the program counter address goes out to the address bus. Of your storage, which I will label as RAM. Is that getting through on the screen okay? Yes. So now we think about it, what's really happening is we've got another finite state machine, which is helping us to, say, drive this finite state machine. Once the address goes out onto the address bus, and it's been out there for long enough, because of access time restrictions that RAM always has, and it's never instantaneous. It could be very slow. 450 nanoseconds later, the data from the RAM is guaranteed to be valid, because access time. And so data comes out from the RAM onto the so-called, data bus. Computers work this way, right? So here comes the data that he's asking for. And what does the CPU get? It's the instruction pointed to by the program counter. So the program counter is effectively the finger that points at the paper that says, read this. And then as you advance, you move your finger down. So the program counter is just the finger that points to the paper. That's all it does. And so then what happens here is that after you've taken the program counter's address, put it into RAM, and gotten your instruction, is you have to increment the program counter automatically, just +1. Give it a clock pulse. That'll get it to the next address. Here comes the instruction. Program counter gets advanced. CPU decodes the instruction to figure out what it's supposed to do. Executes the instruction, whatever that instruction may be. And then it has to do a store. And the store might be to a location. That location is something that the CPU has control over because it too can access the address bus, but not at the same time as the program counter. So it needs a 2-to-1 mux. So it can control who gets the address bus. And so what happens there is the 2-to-1 mux needs a controller, a memory controller, which is part of the CPU, to proceed to tell it whether to listen to program counter or the CPU, because memory here is being used to store not just instructions, but data. They share the same RAM. When this happens, and not all computer architectures work this way, but when instructions share the same RAM as the data, we call it a Harvard architecture. No, I'm sorry. We call it a von Neumann style architecture. Von Neumann style. I got it mixed up. Sorry. Von Neumann. Von Neumann, he worked in 1943 as a consultant with Markley and Eckert on the ENIAC computer, a computer that was the first general purpose electronic computer. It was 18,000 tubes. It weighed tons. It took 2 floors. It took enough power to power a neighborhood. It was touted in the New York Times as being a giant electronic brain, but of course it had less power than a pocket calculator. And it had an architecture that inspired von Neumann, and in fact, Eckert and Malkley were going to build a computer just like this. And what von Neumann did was he created an Institute for Advanced Studies computer over at Princeton, which we now term the von Neumann architecture. But in fact, it's kind of attributing to von Neumann a little bit too much credit because Eckert and Malkley worked really hard on this architecture. He just happened to publish first. And Eckert and Malkley were so concerned about patenting, they didn't want to publish. So von Neumann ended up getting the credit. Which is too bad, too bad. So the alternative computing architecture, this, by the way, this is the architecture you could expect for your iPad, your laptop, and your iPhone, and your desktop. This is the common architecture. But there's another architecture, the competing architecture, called the Harvard architecture. And what it does is just like this, only with a difference. Instead of having just a program counter, it has a data register. And that data register is used for storing, and I'll use a different color to show that this is a competing architecture. It's for storing the instruction. And so the data register will store based on wherever the data register is pointing to. It can have its own RAM. And the reason why you might like to have separate RAM for the program than you have for the data is because data can be stored in a place which we regard as volatile. When you lose power, the data is gone. But for the embedded system, like the Arduino, we would like the data to be stored in a place that is not volatile. And so instead of RAM, we want programmable read-only memory, or what we also call PROM. Right? Now this is being written in blue because this is the competing architecture. Now, when you program your RAM at the factory, we call it PROM because you can't reprogram it in the field. If, on the other hand, you can use an ultraviolet light with a little glass window on top of the chip to erase the PROM, we call it EEPROM. If you can use an electrical pulse, like on a flash drive, which uses an electrical pulse, to rewrite the programmable read-only memory, we call it double EEPROM. And if you're using an Arduino, that double EEPROM is built into the chip. So here's a trick question which instructors of that class, and that wouldn't be like me, would ask their students. And the question is, what operating system does the Arduino use? Anybody know? Operating system with the Arduino? How about you Zoom people? Can you hear me okay? Zoom folks? Zoom folks, how many Zoom folks are there? There's like a bunch. You guys can pipe in, you know. Yeah, you can hear me, good, good. So what is the Arduino operating system? Anybody know? Little microcontrollers we use in the microcomputer class? Well, it's a trick question. There is no operating system, right? And this is surprising to certain people because they say, how can you have a computer? It's crazy. It violates the social norms. It's like putting on your shoes and socks in the wrong order. You walk around and your socks have been all wet. So why would you do that? Well, it has no operating system because as soon as you turn on the computer, it starts to run the program in the double EEPROM. And so that program runs without an operating system. And this is so important, right? Because if your car needs to boot Windows in order to turn on, you're in trouble. If your dishwasher needs to boot macOS in order to wash your dishes when you hit the button, you're in big trouble. So you need computers that just work when you turn them on. We call these embedded microcontrollers because we put them inside of something. if I had to have my druthers, I would take apart this little Logitech camera. I'm holding this up for the Zoom folks. And I would proceed to take it apart. And what would I find inside? A little microcontroller. So that when you turn it on, it can power this little USB, that's a universal serial bus connector, and then proceed to stream video and compress the video on its way out. And that's so important because the video is like HD, and these little connectors don't really have the ability to accommodate HD because this particular one is just USB 2. So they have to step on the video pretty good with compression before they can send it out to the desktop computer, because there are limitations for bandwidth there. So that's a bird's eye lowdown on the computer architecture caper. Two completing architectures subtly different. A finite state machine that's taking data from one side and storing the data on the other, or taking data from one side and just storing it in a different place in RAM. It's so dangerous to be a programmer where you have access to both the data and the instructions in the same place. Why? Because when you're a C programmer, you got a pointer to point to where the data goes. That's just like this data register. And when that data register overruns your program, then you say hi to Dr. Watson in the blue screen of death, because now your program has basically crashed the computer and the operating system is basically hosed. And the only thing that's going to protect you from crashing the computer violently, irretrievably rebooting itself is if you can protect the memory. And so we have a separate operating system architecture called protected memory, which is supposed to keep you from writing crap all over your own program because you were a sloppy programmer. And this can happen easily. And all you have to do is have a stack that keeps going, right? And the stack is, you keep pushing data onto the stack. Maybe you've got a memory leak. Maybe you've got badly written code. Maybe you just have too much data. And it comes on in, and the stack keeps growing until it reaches a critical point in your operating system, and then bad things happen. Crashing, and Xcode spitting out all over my nice clean floors, and I don't know, whatever. You know, things just don't work right anymore. So it's important to think about reliability in this case. If I'm only storing data, you know, in a different area in hardware, I can be assured that I'm not going to overwrite my own program. And we don't like it when programs start overwriting themselves, unless it's something you really think that's something you want to do. Because that is hard, making programs that write themselves. It's interesting. Hard, but interesting. But another topic. So that's the bird's eye lowdown on the von Neumann versus Harvard architecture paper. Von Neumann was at Princeton. Harvard, of course, is another Ivy League school that you may have heard of. And you could say it's the battle of the Ivy League architectures. Yes?
This isn't related to what you're talking about now, but just out of curiosity, you know how you sent out an email this morning saying that when we're not in class, we should join a Zoom because you're going to be teaching a different lecture?
Yeah.
Is the lecture that you taught last class the one that we weren't in person for? Do we have to catch ourselves up on that, or is that what you're teaching right now? Yeah.
No, the lecture I taught last class is a different lecture than the one I'm
so we
teaching
shouldn't
now.
have, okay.
So you want to, I mean, if you weren't here last time,
Well, you said that we didn't have to join the Zoom if we weren't in class. You just sent out the email this morning saying that. I was also confused. So we didn't know that we had to join the Zoom for the last class that you taught because you said you would be teaching the same thing both days.
yeah, that turns out there's so much material, I'm not able to teach the same thing both days.
So was that lecture, did you record that?
Yes, I did.
Okay.
Yes, I've been recording the lectures. I'm recording this one now using the desktop PC and inputting the data with the iPad because I'm told that the desktop PC will give us better quality. This last time when I looked at the lecture, it was like 640 by 480 pixels, and I said, this looks terrible. And then I had the conversation with ITS today, and they said, well, if you use the desktop to do the recording and use the iPad as your camera and your microphone, then it'll be better. Maybe. I hope. So that's what I'm trying today. But yes, if you missed the lecture from last time, what I tried to do was I tried to go over the homework. And so I tried to, let's say, more thoroughly cover any questions people might have had for homework 1. And then I proceeded to cover topics that were in homework 2. And we were talking about the Mealy machine versus the Moore machine. And so from that point of view, if I went back and started doing that again, I'd probably bore some of the people out here on Zoom land because they just saw that lecture because they were sitting in on class.
So are they on Java, the recorded ones?
Yes, yes, I sent a link in that email that shows you how to get directly to the computer architecture class. In fact, if you go just to the docjava.com website, you'll see a whole bunch of other classes too, including Digital Design 1 and lectures from the original, you know, I'll say Moore versus Mealy machine diatribes. So I had, you know, you can imagine multiple. You were probably in architecture class, digital design class with me, right? So you know how I ramble on about chapter 9 and chapter 8 and cats. That's essentially what we're trying to summarize here in homework 2. And so homework 2, I think we kind of beat it to death last time. And so I thought I would talk a little bit more about, you know, some of these interesting topics in architecture because, well, because they're relevant for us. They're relevant. And therein lies, I think, one of the things that you see in architecture classes is why is one thing better than another?
Did you only post homework 2?
No, somebody asked me that. And in fact, what I didn't do was post it. And I said I wouldn't use class time to post it, but
Okay.
I could probably get online and post it real quick right now.
No, that's okay. I just wanted to make sure.
I believe I have to go into myfairfield.edu to do it. And if I click on Blackboard, he says I have to log in again because everybody loves Blackboard. And then if I go to courses, I'll just make sure it's posted right now. Computer systems architecture, because you're in the class and you probably want to see this homework. You may even have questions about the homework, so I mean, it's legit. Let's see. Edit test options. Today is the 10th, so what we'll do is we'll make the homework available and then make it due 17th end of day. And we'll give everybody 2 attempts so that you don't have to accept the first grade if you don't want to. And then what we'll do is hit submit. Okay. I think you should see homework 2 now available on Blackboard. See if that popped up for you. It did? Okay. So now if you want to, you can look at homework 2. It kind of looks, I'll hold it up for the Zoom audience. You should be seeing something that kind of looks like this. I don't know if you guys can see it. I hope you can see it. And then you'll see probably a picture of, yeah, I'll hold it up for the Zoom folks. A picture of Kronos. He's depicted, I mean, well, let's say, how did he pose for this? He's a fictitious person? Well, maybe not. We don't really know. But he's holding up the hourglass, so you know he has something to do with time. And he's got the scythe in there, so that probably means he's a happy, fun guy at a party. And he's got wings. I guess that means he's some sort of an angel or something. The angel of death, I would guess. Always fun to have him. I don't know if you saw the Monty Python movie Life of Brian, but I think the angel of death came to visit during the dinner party, and everybody dropped dead. And they said, "What happened?" And they said, "It was the 7 moose." So, yeah. Guess you had to be there. So there is a compelling argument here that some of the stuff you learned on digital design is actually worth remembering because it's being used here again. And so we've got, well, all the stuff you saw before popping up to bother you again. And there you have it. And if you had any particular questions about this homework, we can certainly cover them either in class today or next class. But I actually covered a lot of this in the last class and recorded it. So you should be able to watch that recording if you like. And I'm sorry for the fact that I couldn't just duplicate lectures, but I came to realize that we weren't going to cover enough material if I did that. And it was just not going to work for us. And part of it is we're still learning what it's like to deal with this pandemic and hybrid distance learning. And frankly, I don't like lecturing with a mask, but I got to. And I don't like splitting a class, but I got to. I mean, it's just, you got it. You got to be safe. Better safe than sorry, right? So that's the way we're rolling. So we're learning as we go. Sorry about that. What can you do? So anyway, here we have this wonderful sort of depiction of the von Neumann architecture versus the Harvard architecture. So the Harvard architecture is characterized by separate data memory. And the Arduino is the example that you can cite that is the common example you're already familiar with. Microcontrollers like to have separate program memory from data memory because they want their programs to just run. Just want everything to just work. So then, when we think about it, there's 2 different schools of thought here, aren't there? But they're not that different. There's another disparity, I'll call it dual, maybe, between designers. And it has to do with this idea that's implicit that we didn't talk about, known as the instruction. And the instruction is a fairly low-level instruction. It can be as simple as jump to this address, add 1 to the accumulator, complement and increment the accumulator, do no operation. In fact, the PDP-8 had 8 instructions, the ultimate reduced instruction set computer. But it was a simple mini computer. And it cost less than $10,000 back in 1965, when computers were mainframes that cost tens of thousands of dollars or millions of dollars. And what you have now is 2 kinds of architectures, Harvard versus Princeton / von Neumann style architectures. But you also have something else that's disparate from Harvard versus von Neumann, and that is RISC versus cisc. And you're going to read all about that in Patterson versus Hennessy, Patterson versus Hennessy. That's good. So as it happens, when we think about RISC, we think about the reduced instruction set computer. We're going to limit the number of instructions. That's what RISC stands for. When we think about cisc, we think about the complex instruction set computer. That's where you have lots and lots of instructions. Turns out, if you have Intel or AMD inside of your computer, you have a cisc machine. Lots and lots of instructions that have to be handled. And the decoding of these instructions, which is done over here in the CPU, leads to a rather more complex task that can take multiple clock cycles in order to be able to do the decode and execute. How many clock cycles, you might ask? Well, the Motorola 68000, which is in the Mac Plus ran at 8 megahertz and took 154 clock cycles in order to do an unsigned integer, 16-bit integer multiply. So the multiply rate was 8 megahertz divided by 154 cycles, i.e. not that fast, right? It had to go through a little operation. It took a while before it could do a simple multiply. So it was slow. If you use a reduced instruction set computer, you can get it so that one instruction operates in one clock cycle. So if you've got a 2 gigahertz machine, which is likely because that's common now, you could have it operate 2 giga instructions per second, which is remarkable. You don't have to, say, oh, that's a complicated instruction, and then it takes many, many cycles. So the goal of reducing the instruction set is to reduce the total size of the lookup table needed to find instructions. It's also to make it so that the instructions are so simple, you can execute them in one clock cycle. RISC versus cisc. Well, as it happens, that is a basic, I'll say, design decision when you do computer architecture. Basic design decision. And you will find that there are a few different trade-offs that go on between these two things, RISC versus cisc. Can you think of an example of a RISC machine? Anybody know of any reduced instruction set computers that you may have encountered? How about reduced instruction set computers in this room that are running right now? They're here. Can you see them? You have eyes, but you do not see. So as it happens, the RISC machines that we have here in the room are hidden here in my pocket. This iPhone, for example, is a reduced instruction set computer. This iPad, for example, is a reduced instruction set computer. In fact, the Acorn RISC machine, which originated as an Acorn computer in the United Kingdom, is responsible for the majority of RISC machines that we are encountering here in the classroom, because what these guys do, ARM, is a business model whose output is intellectual property, IP. They do not make chips. They make chip designs. And they license those designs. And the people who want to put a computer that's well supported with compilers and all the other things that you need for a computer, these people borrow those designs and they embed the designs. And the designs are embodied in a hardware design language, like Verilog or VHDL. And they will give you the VHDL, and you can take that ARM processor and you can put it into your DE2 board's FPGA. That's if you take advanced digital design. I don't know. Has anybody here taken advanced digital design? You do that. Well, if you take advanced digital design, you'll learn about field programmable gate arrays. They'll take in hardware design language. That's the IP that may come out of the ARM company, and they will implement the CPU. They will get it so that it can run right on some hardware. As it happens, if you have a business model based on licensing, which is what you're doing here, you get a very low, what's known in business as marginal unit cost of production. Marginal unit cost of production means how much does it cost to add one unit? If it's low, the cost is low. If it's high, the cost is high. How much does it cost the university to add one student to this class? It's pretty low. How much does it cost to license to one more customer? Not so much. It's got a real nice profit margin. Licensing to 1 million customers costs as much as licensing to 100 million customers. That is, you get an economy of scale. Different business model, right? This is what's known as a fabless semiconductor company, right? What fabless means they don't fabricate anything. They make intellectual property and license it. Why would you want to do that? Well, along comes Broadcom. And Broadcom, well, they are a fabrication company. They make chips that go into products that they want to sell. What do they want to sell? Well, they want to sell $20 internet appliances like routers at Best Buy by the forklift platinum. I mean, they want to make mass-produced consumer electronics. And so what they do is they take the ARM product, right, the CPU for ARM, and they surround it with mixed mode semiconductors. Mixed mode means analog plus digital. So the chip will have something in it like the Wi-Fi radio. You getting that over there in the video? Okay. And let me bring that up here so I can see what it looks like without seeing it backwards. Yeah, there it is. So you got the Wi-Fi. You might have an Ethernet in here so that you can have a little Ethernet switch, and this will act as an embedded system whose job it is to do nothing but manage the networking inside your home. And they love to do that sort of thing because by doing integration of the radio plus the Ethernet and then putting in the CPU that has some firmware in it that just runs, Broadcom is able to bring a product to market that uses less power, is really, really cheap, and has fewer chips, and is easy to manufacture. Along comes Apple. Apple says we want to make phones, and we want the phones to be able to work for longer than 5 minutes. If I put in an Intel CPU that runs in a laptop, 5 minutes later, you're not going to be able to make a phone call. So Apple says, we're going to do the same thing Broadcom does with a difference. We're going to borrow the ARM processor, and we're going to surround it with a bunch of customized stuff that's going to drive a touch screen and drive a cellular network and drive Wi-Fi and do Bluetooth and this, that, and the other thing, a camera. And then at the end of the day, we'll have packaged a system that's very consumer friendly and isn't going to consume 67 watts like a laptop does and gives you 2 hours of runtime, because nobody wants a phone with 2 hours of runtime. So if you wanted to have, sort of who wins the arms race, the reason why ARM is dominating the mobile market is because they're not going to sell you chips. They don't want to sell chips. They want to sell this, intellectual property. They want to make the profit margin for licensing. And maybe they only sell the intellectual property for $1 a unit. They're good with that because that's pure profit for these guys. The only R&D budget they have to have is the one for engineers who come up with the next generation of the ARM processor. This is why ARM is winning the arms race. So this is a basic design philosophy that has been, let's say, freed by a business model that doesn't require a lot of capital equipment. Right? This is kind of cool, actually. Because what? Because Intel and AMD are in a battle. And they, too, are having a war. And in this war, it's a zero-sum game. The number of desktop computers has not changed. AMD's stock is going through the roof. They're taking market share from Intel. They got 17% more market share than Intel this year. And Intel lost 17% of the desktop market. Why? Because of the rise of Ryzen, right? So look at this conflict, right? It's this basic conflict in computer architecture, which has impacted an entire industry, right? And what does this mean? It means when you, the computer buyer, wants to go to Walmart, you have to decide if it's Intel inside or AMD inside, and otherwise it's dark in the box and you don't care. You just don't care. Does it run my applications? Does it run my operating system? Is it cheap? Is it fast enough? That's all I care about. The The designs have gone right down the flusher because all you get is a box in a cardboard box, a box in a box with packing. They call it dunnage. And then what? You have to make a decision. AMD versus Intel. Different businesses, different companies, different business models. AMD had 250,000 square feet worth of clean room space, which they sold. So what do they make? Well, interesting. They take intellectual property, but because AMD wants to sell you chips, what they do is they outsource the fabrication of the chips. So they send the intellectual property to a manufacturer of chips, like Taiwan Semiconductor. And then Taiwan Semiconductor outputs chips, which AMD can sell. They don't need to operate a semiconductor fabrication facility. That frees them to focus on the intellectual property. But they still have a marginal unit of cost of production, which is really rather higher than a licensing business model from ARM. So let's think about this. What does Intel do that's different? Well, Intel keeps $250 million in cash, burning a hole in their pockets. And in their annual report, they say, that's a strategic asset. What do you need it for? Who wants to keep $1 billion worth of, $250 million worth of cash in your pocket? And the answer is, we have to keep upgrading 1 million square feet worth of clean room space. Holy mackerel. Who runs 1 million square feet worth of clean room space? That's expensive space. But that's the Intel model. And they have a big, what they call, CapEx. Capital expenditure, in order to be able to keep their clean room space up to date, is big. And you got to do it if you're going to run a clean room. This is why, right? This is why AMD decided it was going to outsource all its fabrication. AMD becomes fabless. It's a fabless semiconductor manufacturer because it outsources to contractors. Intel, on the other hand, has this enormous CapEx in order to keep 1 million square feet worth of clean room space going. And what do you suppose they put in that clean room space? Anybody know?
The machines,
Yeah, what kind of machines?
lithography machines.
Yes, exactly right. Lithography. Lithography is interesting. Litho is a prefix. Anybody know what it means? Lithograph? No? It means stone. Isn't that interesting? And graphy, what's that? Cryptography, lithography, cartography. Cryptography is encrypted writing. Cartography is map writing. What's lithography? Stone writing. So what you think about with stone writing, and this is kind of an interesting traditional thing that people did. You take a stone, you carve your initials on it, you get the ink roller, you roll the ink over it, you take the stone, you stamp out the paper. We call that printing. It's a form of printing. Turns out you can etch a copper plate, mount it in a printing press, hit it with an ink pad, and then hit it on top of a piece of paper, and that is called a printing press. And if we think about it, that's exactly what they did with the Gutenberg Bible. They would lay out the letters, and then they'd roll on the ink, and then they would just get a big sort of wine press and piece of wood, and they would press the ink on top of the wood, and then they would press it into the, they would put paper there, and they'd press the paper onto the letters, and they would print out a page. Revolutionized the printing industry in think it was 900 AD or something like this, right? Dark Ages. They were coming out of the Dark Ages. They invented writing and printing. No, they didn't invent writing. They invented printing. So this is a big time invention. Then what you do in front of the lithography is you put the term photolithography. So now you're using light to do the writing. So imagine if you were in the dark room of the old age when they had film, and you had an enlarger, you'd take a negative and you would shine it onto a piece of sensitized photo paper, and that would imprint an image. This is how dark rooms used to work. I used to do this. I know. But here in the new age, what we're doing with semiconductor photolithography is we're not using a sensitized piece of paper. We get a piece of silicon the size of a dinner plate, 200 millimeters in diameter. And we sensitize it with chemicals. And then we, in a vacuum, hit it with soft X-rays, which are being shined through complex optics onto the dye, the little chips that are inside of the wafer. And then we take the whole wafer and we put it into a cutter and we cut out the little chips. If you're Intel, you can sell one of those little chips for $2,000 each. No kidding. That's a server, Xenon server on steroids. They're a top-end chip. Only Intel gets away with charging stuff like that. It's got a real poor yield, which means there's a lot of chip failures. But when it works, it's fast. And entities like Amazon for their regional data centers, or Oracle for their cloud services, or Google for their cloud services, they're going to buy those things. And they're going to buy them, and they're going to buy them by the forklift plan. And Intel will make a mint selling it. So that's an interesting market, and Intel tries to capture it. That's called the server market. Server. Interesting word. What is a server anyway? Server is any computer that provides services to any other computer. So I say, Patterson and Hennessy, they say, oh no, it's a big thing and it's expensive. And I say, no, it's not. It doesn't have to be. I can serve files from my laptop in my closet. I run Unix on it. It has a program that runs in the background called HTTPD, which is the Hypertext Transfer Protocol daemon, also known as a web server. It's a server. It's just plain vanilla, ordinary laptop. You can do it with a $35 Raspberry Pi. You set it up as a server. It's not a particularly good server, but it's a server. And so anything can be a server, I say. A server is just a role. It's not a title of computing power. It's just a role. So now we have sort of an interesting ecosystem, right? It's an ecosystem in the industry. We have the fabless semiconductor manufacturer versus the heavily capitalized Intel. We have the intellectual property manufacturer, ARM, versus Intel and AMD, the upstart, right? This is like, I don't know, David versus Goliath. And these are like two bullies kicking sand in each other's face at the beach. And these guys are just saying, well, we're going to take a different path, the path less trodden. And they do great with it. I mean, this is fantastic business to be in. And the three different companies have totally different business models, right? AMD probably want to sell chips, that's true, but they're not going to do this kind of CapEx in order to create the semiconductor fabrication facilities needed to do it. They'll go to Taiwan Semiconductor or the lowest cost bidder. It still doesn't explain how AMD is able to take market share away from Intel. How do they do that? I mean, everybody knew Intel. Everybody wanted Intel inside. Why doesn't it continue to dominate? I don't understand. Can anyone explain? I challenge you. You come up with an idea. I've been chatting for too long already. So you active learning, you tell me. And Zoom people, hi Zoom people, you can tell me too. I think I can hear you guys. If you have an idea why AMD should have Ryzen and why Ryzen should be any better than anything Intel comes out with. I mean, if I said, what do you want, Ryzen or Xenon? it's like, spandex or booga booga. How do I choose? Right? It doesn't make any sense. There's got to be a reason. The Zoom folks are silent. Can you guys hear me okay?
Yes, we can.
Okay, just checking. Thank you. So I will tell you if you don't tell me soon. No ideas? Okay, well, here's the answer. Intel is stuck. They're stuck at 14 nanometer design rule. And this is a big problem. Design rule is the smallest feature that you can express using photolithography onto the semiconductor. And what happens is it reflects the total number of transistors that you can put into the chip. Meanwhile, AMD said, we don't care how you do it. All we want to do is get the smallest possible design rule possible. And Taiwan Semiconductor has been able to do it, their contract manufacturer, and they will give you 7 nanometer design rule, which means you can have cheaper chips because you got more transistors. Yes?
So is Intel just not keeping up with Moore's law?
That is exactly right. Yeah, the question for the Zoom folks is Intel just not keeping up with Moore's law? And of course, what you want to do is you want to sort of take it back, step back and say, what is Moore's law? It's not really a law. I mean, you know, what happens if I break Moore's law? Do I go to Moore jail, or maybe they throw me into a Moore machine? Oh, that sounds painful. So what you know, Moore's law is just a rule of thumb that we would expect computers to, let's say, double their transistor budget every 18 months. They used to say double in speed every 18 months, but they're no longer trying to sell computing based on speed. In fact, the mere mortals, see that they've shifted how they sell computers. And that's a slightly different discussion, which we're going to get into shortly. So that right there, 7 nanometers versus 14 nanometers, means Intel has to play catch up. And Intel has a tick-tock rollout on their product line. Tick, they increase the speed of the CPU. Tock, what they do is they change the architecture and the total number of transistors in the CPU. And they kept trying to do that year after year. And eventually, as they say with Moore's law, they kind of ran out of steam on that one. They've got to get up to speed. They've got to get up to speed. And if you go to ASML and buy one of their twin scan machines, which are terribly expensive, you can get a soft X-ray machine, which is called extreme ultraviolet light. And it's going to emit exquisitely small wavelengths. I think it runs around 13 nanometers. And they use a light source, which they call the Cymer light source. And what it does is it takes droplets of tin in a vacuum and hits it with an infrared laser, and it causes them to emit the soft X-ray at an extraordinarily intense radiation amount so that you can expose your chips and get good throughput. The goal is to get so many dinner plate sized wafers out of the machine in a given period of time. So that's a reason why you could have the rise of Ryzen, but there's something else going on. People, because they couldn't keep making their CPUs faster, had a problem. And the problem is thermodynamics. Most computations dissipate a lot of energy. And you can drain the heat with water, but there's a better strategy. What they do is, instead of making everything faster and increasing the thermal appetite for their CPUs, is they just added more and more CPUs. And so this has led, before we had an arms race, and now we have something else. We have what I call the core wars. They're selling CPUs based on the total number of cores that are in them, right? So I got what do they call this? Raspberry Pi, right? Raspberry Pi 1, 2, and 3 had one core and ran at 32 bits using a Broadcom CPU. Raspberry Pi is a little $35 single board computer. I have too many of these, more than I know what to do with. And then they came out with Pi 4. And Pi 4 had 4 cores. It was a 64-bit machine. And by the way, no longer $35. And so, as far as single board computers are concerned, what are they trying to sell us here? And the answer is, well, here's something with wider bandwidth for the data bus is 64 bits, and more cores. Ooh, more cores is good. I like cores. Cores are great. So that means they got extra CPUs. And presumably, that makes the machine faster. When doesn't it make it faster? When you can't find enough different processes to work on the different cores. And if you've got cores that are idle and you want to try and save a little energy and cool down the chip and consume less electricity, you can shut down a core. This is what they do. They shut down cores. Along comes AMD and Intel, and they're using multi-core systems too. And the top end on some of these processors is 64 cores. But there are diminishing returns in adding cores in order to make things faster. Because unless you have enough CPU tasks to run on these chips, you're not going to be able to make good use of all the cores. So what do? Is they create these so-called CPU servers, and they run virtualization programs like VMware. And what that does is it gives you an operating system that can run inside of one of the cores, and then you can have another couple of cores run another operating system, and then you can have it run in your regional data center. And when somebody like me wants a micro instance of an elastic computing server from Amazon Web Services, I reserve one of the cores in one of these big server-sized CPUs. And so that actually works out pretty good for Amazon. It also works out pretty good for people who are looking for little single board computers, but might need 4 cores because you got enough tasks running. But eventually, you run into a company that goes absolutely bonkers with the cores. In comes a whole new architecture. NVIDIA. And what do? Well, they're not making general purpose CPUs. They don't want to. They've gone down a different path. They've gone down the path of creating many, many cores that are able to effectively do one thing reasonably well. And they call this architecture CUDA. And what they'll do is they'll have thousands of cores. But it's specialized and it's hard to program. And I've got a few of the so-called general purpose computing Tesla cards. And what they do is they have the temerity to call these things personal supercomputers. And somebody has to say, I understand what personal is, and I think I know what a computer is, but what makes it a supercomputer? And the answer is, well, it's quite a bit faster than a desktop computer, but it's not general purpose. It's really good at graphics. And you can even use it to mine for Ethereum if you want to and make cryptocurrency pop out. And it consumes lots and lots of power. I mean, I've got like a little space heater in my office, and if I turn it on, well, I share a circuit breaker with my next door neighbor, and he has a hot pot. And when he turns on his hot pot, circuit breaker blows in microseconds. And then you have to wait a really long time because the circuit breaker's in a closet and we don't have the key. And so what that means is we're sitting in the dark because Professor Lyon has a fancy graphics card, and the fellow next door, who shall remain nameless, has a hot pot. And he thinks his hot pot is more important than my graphics card. So that ends that discussion. So as a result, I can't use my little NVIDIA card, interestingly enough. And some of these cards take 1,500 watts. That's like a hairdryer. And then if you bought a dog breath CPU where the card actually fits from Walmart, first thing you're going to do is tear out the power supply unit and put in something beefy, because Walmart's not going to sell you a computer with more than 350 watts pumping out of the power supply unit. They're targeting a different market. They're not targeting, see who wants this? It's not even the people who are interested in scientific visualization like me. It's the people who are gamers. Those guys, girls or whoever, they want to do what they call massively multiplayer online games, also known as first-person shooter games. And I guess they spend a lot of time doing it. And that's where the real money is. Because talk about low marginal unit cost of production, being a game manufacturer is great, because you don't even have to ship a box with instructions. You just say, oh yeah, here's your code, go download it. And your market's bigger too, right? Because the game market is ginormous. Even compared with the ARM folks, that's a great market to be in. And a licensing model too. Very scalable. So when you're learning to be a CUDA programmer, I guess you get cooties or something, but you learn about the architecture that's internal to the CUDA processor, and then you try and get the little CUDA cores to communicate without too much overhead. Because if you have to have cores communicating with overhead, that overhead will kill your process. It will essentially limit the speed up that you can experience. Why? Well, because what happens if you have one CPU, you run at a certain speed. If you had two, you would like it to run twice as fast, but it doesn't work that way, right? Because the two processes, you know, if it's a, imagine, if you will, a divide and conquer algorithm like Quickstore. You take the left-hand side of the list, and you sort it. You take the right-hand side of the list and sort it. And then at some point, you got to merge the two halves. Well, that's where there's going to be a fixed amount of overhead, because you're going to have a separate CPU doing that. So you can split and merge only so many times before you run into an inherent limitation in terms of how fast you can speed up. You know, maybe adding 2 processors will make it almost twice as fast, but having 10 processors isn't going to make it 10 times faster. It may only make it 5 times faster. And 100 processors, well, maybe it only makes it 20 times faster. They're diminishing returns for certain algorithms. Now, having said that, for the embarrassingly parallel computing algorithms such as image processing or computer graphics or computer vision or mining Ethereum, then CUDA might be ideal. Even for dedicated processes like fluid dynamics, gas simulation, that CUDA might work great. Now, when you look at the list of 500 fastest computers in the world, a lot of times what you'll see is NVIDIA is a big role in those computers. And they come in and they do things like TensorFlow for neural networks. And it's good at that. It's all right with that. And so as a result, it's kind of a killer application for these guys. But it's not a general purpose computer. It's different architecture. And if you can create a specialized architecture for which there's a nice market, then you can essentially dominate that market. And that's what NVIDIA has done. Turns out, they're kind of off to the side over here doing their own thing. Their competitor is a Canadian firm known as ATI. And we don't hear much about them anymore because they were engulfed and devoured by Intel. Intel wanted graphics to be a part of their their portfolio. So as it happens, NVIDIA is still a standalone company and makes a nice name for itself. It's hard to value a graphics company after it's been, let's say, bought out by a larger company. So that's the brief rundown of the computing ecosystem as I understand it. I have two basic different kinds of architectures, Harvard versus von Neumann. I have two basic different kinds of instruction sets, cisc versus risc. Then I have three completely different business models: the fabless semiconductor manufacturer, the high capital expense Intel, totally leveraged, and then here comes ARM making nothing but intellectual property. And then over here on the side, with much smaller market really, is NVIDIA, doing its thing with specialized computing and trying to scratch out, actually they do it very nicely, and create a living with graphics cards and with, well, specialty scientific visualizations. So that's an interesting idea. The fellas who do the Raspberry Pi, they deserve special mention. They're trying to target a mass market at a very low cost, which means their profit margins are thin. How does one bring a computer to market for $35? How does that work? How much do you really make? Right? Marginal unit production is high, cost of distribution is high, your profit margins are low. This is very difficult. Is there a question out there at Zoom land? Sorry. So,
Sorry, dude, the legs work out.
Yeah.
Like, let's see how much pussy you
You're gonna have fucking.
could you mute yourself if you're not participating in the discussion?
Kelsey doesn't go to the edge. It's easy there.
Oh,
It's
fuck.
like you guys in the road.
I just followed her on Instagram.
Really?
Yeah.
Guys? Can I mute you? Sorry, Bashir, I just muted you. You were chatting. If you want to unmute yourself, you can.
I'm sorry for that first.
That's all right. It's just thought you had something to say, that's all. If you do, go chime in. That's the design philosophy. Let me see what's going on here. We got the core wars. We got AMD versus Intel. We got cores being marketed to the mass public. What happens inside of the CPU? I don't think anybody knows. I mean, if I told you there were 4 cores and a Northbridge processor in the Needham, you'd be like, what? Who? Where? Nobody pays any attention to these code names that are coming out of these companies. And they're doing a very poor job of educating us in terms of telling us why I should have Intel inside. And I'm a guy who's been doing this for the last couple of 3 decades, and I can't tell you that Intel is better than AMD, or AMD is better than Intel, or that ARM is better than, you know, any of the other two, or that RISC is better than cisc. I can't tell you that that's true because I don't really know. It all depends. And industry shifts from time to time. For example, Apple started with the 68,000 with the Mac Plus. Actually, it started with the 6502 with the Apple II, and then the 68,000 with the Mac Plus. And it continued to go on to the 68030 and the 68040 and the Quadra systems, and then migrated away from cisc and went into the so-called Power PC. And they said, we're going to do reduced instruction set computing. And they kept doing that for years. Then they said, you know what? This isn't going anywhere. Motorola isn't moving it forward. IBM's not moving it forward. And so then they said, you know what? We're going to jump on the Intel bandwagon. And they put Intel inside of all of their desktop computers and laptop computers. But then, for reasons that are now clear, they switched to ARM for their mobile devices because they had to have something that was going to have a little bit more runtime. And they wanted to incorporate all kinds of interesting radios, like cell phone technology, into their ARM systems. Now they're saying maybe we ought to migrate back to RISC on our desktop computers. And when that happens, the operating systems will be changed from macOS to iOS. Everybody's going to migrate to different binaries for their applications. Things will stop working properly, and they'll basically pull the rug out from all the developers. And they've done that before. They did it when they migrated from cisc to risc. They did it again when they migrated from risc back to cisc. Now, if they go back from cisc to risc again, everybody who developed code will find it doesn't work anymore. This is a compelling argument for remaining a Java programmer, right? Because Java guys and girls they'll write code that outputs to bytecodes, which is a machine that's really a meta machine. Java Virtual Machine uses machine codes, machine instructions that run in a virtual machine. And as long as you have support for that virtual machine on your hardware, your code will run. Then along comes Apple, and they say, oh yeah, you see this iPhone? You see that iPad? We're going to outlaw Java on these machines. So when I show up at the Genius Bar with a hacked version of the operating system known as Cydia, which allows me to run Hello World in Java on my phone, because I figure it's my phone, I should be able to run whatever computer program I want to. The Genius Bar throws me up. He says, you violated the warranty. Get away from here. Get away from us with that ad hoc jailbreaking thingy. And really, they call it jailbreaking because they basically don't want anybody to do anything that they don't agree with their computer hardware, because it's theirs. It's not yours. You're just using it, even though you bought it. It's kind of ridiculous to me, because I figure if I buy a computer, I should be able to run any operating system I want to on it, but Apple doesn't agree with that. So this is they call it the EULA, the End User Licensing Agreement. So if you violate the EULA, if you can't do the time, don't do the crime or something, they consider you very bad. So when it comes to computing, I'm a bad man. But there you go. It's just me. And I don't recommend that anybody here do any jailbreaking at all, because it'll just get you into a world of hurt. Do it on a computer you don't care about. So that's a brief rundown of the architecture. I hope that was interesting for you. And it gives you a little bit of insight into really what this course is about. It's not about more machines versus million machines, okay? We've got a whole bunch of interesting things going on in the computer industry. Oh, geez, I've got my thingy running. That's my ARM processor. Let's turn that off. Okay, so that's what I have for you for today. Stay safe. Yes?
On Java for the September 8th lecture, this says homework 1 and 2. When I clicked it, it said this file is not found.
Oh, that's not good.
I wasn't sure if that was like the name of it. Underneath it, it says lecture 2A, didn't look like it either.
Okay, I will fix that when I get home. Thank you.